All right, so let's look at the next example. Example, a 3-meter ladder leans against the wall at an angle theta with the horizontal. If the bottom of the ladder is pushed toward the wall, with the speed of, let's say 2 meter, let's say 0.2 meter per second. How fast is the angle changing when theta is equal to 45 degrees? Okay, see, we have a ladder here, 3 meter long. And it has an angle theta with the horizontal. So what do we want to find? So let's call this one X. So solution. So what is given? The rate of change of X, because it says X is moving towards the wall, right? So X is decreasing, right? At which rate? Rate of change of distance, which is same as velocity or speed. How much is it? It's given as 0.2 meter. So dx to dt is equal to 0.2 meter per second. What are we asked to find there? It says how fast. How fast means rate of change of the angle. Rate of change of angle, which means d theta to dt is asked at theta equals 60 degrees. Okay, see here we have a right triangle. So in the right triangle above, right triangle above, what can we say? We can write a cos theta. What cos theta is? Cos theta is equal to x over 3. So that means x is equal to 3 cos theta. X is equal to 3 cos theta. So what will be dx to dt then? Because dx to dt is given, d theta to dt is asked. So what is dx to dt? Or in other words, x prime. See, I have to use the chain rule now because I have a function of the form cos u. What is the derivative of cos u? Cos u derivative is minus u prime times sine u. So then the derivative of x will be minus 3 sine. My u here is theta. And then times theta prime. Or in other words, minus 3 d theta to dt sine theta. Okay. My u here is theta. And so the formula will be -3 theta prime sine theta. Theta prime is same as d theta to dt. Okay, so we have, so what do we get? We have dx to dt equals -3 d theta to dt. That's sine theta. Now at theta equals 45 degrees, dx to dt, which is given as 0.2 equals -3 d theta to dt times sine 45 degrees. And this is -3 over √2 d theta to dt, which is equal to 0.2. So we want to find d theta to dt. So d theta to dt is equal to 0.2 times -√2 over 3. So this is going to be -2 √2 divided by 30 radian per second. Okay, so still we have, so this is an application of chain rule, an example of chain rule. The only difference is that in the previous examples, we had x as independent variable and then u as a function of x. Maybe I can write it as a remark here. Comparison with previous examples. Previous examples, we had x as independent variable and u as a function of x, dependent on x. Here, t is independent variable, time. And theta is as a function of time is dependent on t. So x is replaced by t, our independent variable is t, which is time, and u is replaced by theta here. So theta is a function of t, and the t is the independent variable. Right? So instead of previously we had, and by the way, y, okay, another thing I can say, and y was a function of u. I can write it here. Here, x independent variable, y function of x, y function of u. Here, t independent variable theta dependent on t, and instead of y here, we have x. I can write it this way. And x is a function of theta here. So do you see the comparison? Just the letters have been changed in a slightly confusing way. I can agree. Some people could get confused because see, t here has the role of x in the previous examples. In physics, in mathematics, usually we say x is the independent variable. In physics, normally we say t or time is an independent variable. Then previous example, we had u as a function of x. Here we have theta as a function of t. And then we had y as a function of u in the previous examples. Now, X has the role of Y in this example. X is a function of theta, and theta itself had the role of U. So if you have this in mind, right, you will see that the concept is still the same, just the letters that we are using are different. So I'm hoping that this does not make any confusion. Okay, so instead of X, we have T, instead of U, we have theta, and instead of Y, we have X. So see here, this X here is like my Y here, this theta is like my U, and this T is like my X. So dx to dt is like what I was saying, dy to dx in the previous examples. And then we have cos theta, but then we said cos theta has the role of U. So cos U derivative minus U prime sine U, which is just replace U with theta. We got this, theta prime is d theta to dt. And then we just use this formula. We use the value of dx to dt. And we use it to find the value of d theta to dt. All right. So we're still in the remaining time of today's lecture. I want to do more examples of this chapter, more examples. The differentiation topic. Differentiation and derivative rules, let me see. Okay. So one is about the concept of differential equations. Differential equation means an equation that relates a function y with its own derivatives. So for example, y double prime plus y equals 0. See, this is called a differential equation because it's an equation that relates a function y with its derivatives. It says that if you differentiate a function y twice, in other words, it says what is the function y such that when you differentiate it twice and then you add it with the original function, you get 0. Is there a function with this property? If yes, what is it? So the goal in the differential equation, the goal is to find all functions y that satisfy a given differential equation. Any function y that satisfies a given differential equation is called a solution. A solution of that differential equation. So DE means differential equation. So for example, consider a differential equation Let's say y double prime plus y equals 0. Show that y equals sine x is a solution of this differential equation. So I have a differential equation, which means an equation that relates y with its derivatives. Now I want to show that a particular function is a solution of this. A solution of this means when you replace y with this function, the equation is satisfied, meaning that y double prime plus y for this particular y equals 0, becomes 0. If I have a function y such that y double prime plus y is equal to 0 for that y, that means that function y is a solution for that differential equation. If y double prime plus y is not 0, then that y will not be a solution. Same concept for the standard equations. For example, when you say r squared minus 4 equals 0, then you say r equals 2 is a solution for this. Why? Because when you replace r with 2, 2 squared minus 4 is 0. Right? But so this is a solution. But for example, r equals 1 is not a solution. Why? Because when I replace r with 1, 1 squared minus 4 is minus 3, which is not 0. So if you have a value of r that you replace it, you get the equation is satisfied, then that's a solution. If the equation is not satisfied, then it's not a solution. Same thing here. If we replace y with sine x and left-hand side becomes 0, then that means sine x is a solution. But if we consider another function that when we replace y with that function and we don't get 0, then that's not a solution. Okay, so the only difference is that when you say r squared minus 4, the potential answers for r are numbers. For example, 2 is a solution, 1 not a solution. But here in differential equation, the potential answers are functions. So sine x is a solution. X squared, for example, x squared is not a solution, right? So instead of powers, here we have derivatives. So second derivative of y plus y equals 0. And instead of numbers, r is a number here. Here y is a function, okay? So differential equation is a type of equation, but what is the difference with the equations that you have seen before? Instead of numbers, we have functions, and instead of, for example, powers, we have derivatives. Still, a solution means a function that when you replace y with that function, the equation is satisfied. So let's verify that this is a solution for this equation. So if y is equal to sine x, what is y prime? Because we want to find y double prime. Y double prime is second derivative, which is the derivative of the first derivative. So y prime is cos x. So y double prime is cos x derivative, which is minus sine x. So y double prime plus y will be equal to minus sine x plus sine x, and the answer becomes 0. So that means y equals sine x is a solution of y double prime plus y equals 0. Now let's say part B, show that y equals x squared is not a solution of y double prime plus y equals 0. So how can I show something is not a solution? Means if I replace y with that function, the equation will not be satisfied, meaning that the left-hand side, when I calculate it, y double prime plus y will not become equal 0. So let's see, y equals x squared. So how much is y prime? Y prime, the derivative of x squared is 2x. And y double prime, the derivative of 2x is 2. So y double prime plus y, which is 2 plus x squared. This is not equal to 0. So when we say equal 0 or not equal to 0, this means as a function. As a function. This one 0 also means as a constant function 0, as the constant function 0. So this one as a function is not equal to 0. But this one is not 0 for every x, right? 2 plus x squared is non-negative. So 2 plus x squared is not 0 for every x. But if this is not 0 even for one value of x, still I can say that these two are not equal as functions. Because if you want two functions to be equal to each other, they have to be always equal to each other. Right? So what I'm saying is that in this example, this left-hand side is not 0 for every x, but even if it's not 0 for one x, I can still say the function is not equal to 0, not equal to the 0 function, constant function 0. So let's say part C, let's say show that y equals x is not a solution. Again, for y double prime plus y equals 0. So see, y equals x. What is the derivative of this function? Y prime will be 1. And therefore, the second derivative will be 1 derivative, which is 0. And so y double prime plus y will be 0 plus x. And this is not equal to 0. For example, at x equals 1, x is 1, which is not 0. So this function here, like I said, okay, seems the screen is freeze. Let me stop share. So y double prime is derivative of y prime, which is 0. Y double prime plus y will be 0 plus x, which is not equal to 0. Like I said, so this function here, if it's not 0, even at one x value, then that means it's not the constant function 0. So this function here is non-zero at many points, such as at x equals 1. So it's not a constant function 0. Okay, now let me give you an exercise. So this means that y equals x is not a solution for y double prime plus y equals 0. Now another, let me give you an exercise. To show that y equals x times sine x is a solution to y double prime plus y equals 2 cos x. Okay, so again, you have to take this function y, differentiate it once, find y prime, then differentiate it another time, find y double prime, then add y double prime with y. And after you simplify and do the calculation, you will see that the answer is 2 cos x. That means y equals x sine x satisfies this equation, meaning that when you replace y with x sine x, y double prime plus y becomes 2 cos x. Now another exercise, show that y equals x sine x is a solution of the equation y fourth derivative plus y second derivative equals minus 2 cos x. Okay, again, take this function, differentiate it 4 times, and then differentiate it 2 times, and differentiate 2 more times, differentiate 4 times. And then you can calculate this left-hand side. You'll see that once you do the calculation and simplification, the answer becomes minus 2 cos x. That means this function is a solution of this equation. Okay, now again, let me say this is part A, and part B, let's say show that y equals, let's say 2x cubed minus x squared is not a solution for the equation above. So this function is a solution for this. This function is not a solution for this. Again, how can you verify? Just find the y fourth derivative and y second derivative, y fourth derivative, add them. You'll get a function. If that function is not equal to minus 2 cos x, even at 1x value, then that means that's not a solution. So if left-hand side becomes minus 2 cos x for every x, then that's a solution. But if it's not same as minus 2 cos x, even at 1x value, then that's not a solution. Okay, so you want to show that this function is not a solution for this equation. So let me give you a remark that you will learn more about differential equations and how to solve simple differential equations in Math 114. So simple solving differential equation means finding y. Remember, the differential equation is an equation that relates y with its derivatives, and the goal is to find y, to find the y that satisfies the given differential equation. Now, how can we find y? How can we solve a given differential equation? Well, that could be a very complicated question. Depends, of course, on the type of the differential equation. So you will learn the details, more details in Math 114. For example, what types of differential equations do we have? For example, you will see that this one is called a second order differential equation because the highest derivative appeared is the second derivative. or this one is the fourth order differential equation because the highest derivative appeared is the fourth derivative, and so on. So that's one way to categorize differential equations. Another way is by saying whether they are linear or no. For example, see all the y terms here have power 1. So they will be considered as linear, but let's say if I replaced it with y squared, this one, then it won't be called linear. So in Math 114, you will learn a little bit about types of differential equation, and you will learn how to solve the differential equations only in the simple cases, very simple cases. If you want to learn more about differential equations, you learn more, and you can learn more, you can learn further in Math 230 differential equation course. You will learn more, how to solve differential equations, not just in very simple cases, but also in rather simple cases. But still, even in Math 230, after you finish the course, still you're in the beginning of the path of differential equation. Differential equation is a topic that has lots of applications, and right now, today, many people around the world who are doing research on this topic. So even after Math 230, you're still in the beginning of this path. If you want to learn more, you can take, higher level differential equation courses, for example, third year, fourth year differential equation courses. Of course, if you want to study math in a graduate level, or even engineering in a graduate level, you still need to, because differential equation has lots of application in engineering and in physics. So even if you want to study masters in physics or engineering, still you have to learn some advanced differential equations in the master's level or PhD level. So yeah, that's a important and broad topic. We just give a very brief introduction to it, and just to introduce the concept, basically. And yeah, so that's one thing. Now let's do more examples. Let's see. So let's say, okay, use the graph of the function above. Example, use the graph of the following function to evaluate d to dx of square root of x plus f of x at x equals -1. So how does the graph look like? So there is a function here. Let's say this point is -3 and 0. And this point here is 4. And this point here is 1 and 0. And this is y cos f of x. Okay, what do we want to find? We want to find the derivative of this function at x equals -1. We said that if the derivative at a given point is asked, first you need to calculate the derivative, the formula for the derivative using derivative rules, and then replace x with the given value, okay? So here we want to find what? So d to dx of, so first find, forget about x equals -1. You want to evaluate the derivative of this function at x equals -1. But for now, forget about x equals -1. Just find the derivative of this function as a function of x. Then we will replace x with -1 later. So first find d to dx of square root of x plus f of x. D to dx of square root of x plus f of x. Well, we have to use the derivative rule for u to power 1/2. U to power 1/2 derivative, what is it? U to power 1/2 derivative, 1/2 u prime u to power -1/2. So then this is 1/2 x plus f of x derivative times x plus f of x to power -1/2. So how much is that going to be? 1/2 times 1 plus f prime of x divided by root x plus f of x. Now replace x with -1. What do we get? So d to dx of square root of x plus f of x at x equals -1 is equal to 1/2 1 plus f prime of -1 divided by root 1 plus f of -1. Okay, now we need to find f of -1 and f prime of -1, and we'll be done. So how can I find f prime of -1? F prime of -1 means f prime of -1 means slope of tangent line at x equals -1, which is going to be slope of, so let me call, if I call this line, for example, let's say L1 and this line L2, then this will be the slope of L1. Slope of L1. Now, how can I find slope of L1? Well, we just need 2 points, right? And then y2 minus y1 divided by x2 minus x1. So is that's going to be, what are the points? So x1, y1 is -3 and 0, x2, y2 will be 0 and 4. So then this will be 4 minus 0 divided by 0 minus -3. So the answer will be 4/3. The slope of tangent line at x equals -1, that's going to be 4/3. Okay, so f prime of -1 is 4/3. What about f of -1? How can I find f of -1? So f of -1 means the value of the function at -1. So this is a straight line, right? If I can find the equation of this straight line as a function of x, then I can replace x with -1 and find the output at x equals -1. So what is the equation of this line. I just need to find the equation of this line. So we need equation of L1. So what is that going to be? So I have 2 points here, 0 and 4 and minus 3 and 0. So, and we know M, we already calculated M. M was 4 over 3. So equation of L1 will be y minus. So if I use the point, for example, minus 3 and 0, y minus 0 equals 4 over 3 times x minus minus 3. So then that's going to be y equals 4 over 3x plus 4. So at x equals minus 1, y is how much? 4 over 3 times minus 1 plus 4. This is 4 minus 4 over 3, which is 8 over 3. So that means f of minus 1 is equal to 8 over 3. F of minus 1 is 8 over 3, maybe I can. And f prime of minus 1 is 4 over 3. So we can find the value of the derivative of this function at x equals minus 1. So that means d to dx of square root of x plus f of x at x equals minus 1 is how much? So that's going to be 1/2 times 1 plus f prime of minus 1. F prime of minus 1 is 4 over 3 divided by square root 1 plus f of minus 1. So square root of 1 plus 8 over 3. So how much is that going to be? So 1/2 times 7 over 3 divided by square root of 11 over 3. Then this is 7 over 6 divided by square root of 11 over 3. So this is 7 root 3 divided by 6 root 11. Okay, so this is the final answer. Now let me add part B for this question. For the function above, shown in figure above, find d to dx of f of 2 sine x at x equals pi over 6. So again, see, f of u derivative is asked. F of u derivative is asked, which we can find it using the chain rule. And then we have to replace the value of x later, okay, after we find the formula as a function of x. So f of 2 sine x, so by chain rule, what can we say? So d to dx of f of 2 sine x is equal to f of 2 sine x derivative. And this is 2 sine x derivative times f prime of 2 sine x. Right, so f of u derivative is u prime times f prime of u. That's exactly what the chain rule says. f of u derivative is u prime times f prime of u. My u here is 2 sine x. So then this is equal to 2 cos x times f prime of 2 sine x. Now, what is the value of x? So at x equals pi over 6, at x equals pi over 6, what can we say? F prime, f of d to dx of f of 2 sine x at x equals pi over 6 is equal to 2 cos pi over 6 times f prime of 2 sine pi over 6. How much is that? 2 times root 3 over 2 times f prime of 2 times sine pi over 6 is 1/2. So this is root 3 times f prime of 1. Okay, so let me assume that this function continues, because if I need f prime of 1, if 1 is the end point, then f prime of 1 will not be defined. But if I assume that this function continues after 1 as well, then I can find f prime of 1 with no problem. So f prime of 1, so what is the answer? Root 3 times f prime of 1. Now, what is f prime of 1? F prime of 1 is equal to the slope of tangent line at x equals 1, which is how much? Which is the slope of this line here, L2, if I call it L2, slope of L2. Slope of L2. How much is that now? You have 2 points again. 1 and 0 and 0 and 4. 1 and 0 and 0 and 4. So 1 and 0 and 0 and 4 are my points. So then this is 4 minus 0 divided by 0 minus 1. The answer is minus 1 over 4. And then therefore the final answer will be d to dx of f of sine, f of 2 sine x at x equals 1 is going to be root 3 times f prime of 1. Root 3 times minus 1 over 4. The answer is minus root 3 over 4. Okay, so next example. Show that the triangle that is formed by any tangent line to the graph of y equals 1 over x with x positive and the coordinate axis has an area of 2 square units. Okay, so we have a function here, y equals 1 over x with x positive. So there you are. Now we are considering a tangent line here. So this is our tangent line. Okay, And we want to show that this triangle here, so let me say OAB has area 2. So suppose that, let me call this one L. So suppose that L is a tangent line to the graph of, is an arbitrary tangent line, basically, to emphasize, is an arbitrary tangent line to the graph of y equals 1 over x with x positive. We want to show that the area of OAB is equal to 2. Okay, so what you have to be careful here is that in mathematics, we said that for proofs, to prove a statement in mathematics, we have to prove in general, not with examples. Okay, so you have to be very careful. Do not give an example of a tangent line here with area of the triangle that forms a triangle with area 2. Your statement or your proof has to be valid in general for any tangent line. So this is a very important thing. You have to be very careful. Be very careful. Your proof must be valid for any tangent line to the graph above. Yeah, any tangent to the graph above. Not just an example. Okay, so when I say it has to be valid for any tangent line, means you are not allowed to give an example of a tangent line that forms a triangle with area of 2. It has to be an arbitrary tangent line. So suppose that, now the argument is as follows. So suppose that the tangent line is tangent to the graph at, let's say, x equals x0. Okay, so this is the important part. Do not say it's tangent at x equals 5, or do not say it's tangent at x equals 2, because the argument has to be valid in general, right? But if I call the point of tangency, the x value of the point of tangency, I can give it a name. Giving it a name has no problem. You know, it doesn't reduce the generality, right? So I'm calling it x0. Now, is this x0 could be 1, could be 5, could be 6, it could be anything. My argument is valid in general because I'm not assuming that the point of tangency, I'm not assuming point of tangency is 1, or I'm not assuming it's 5. I'm just calling it x0 for an arbitrary x0. So suppose that tangent line is tangent to graph at x equals x0. Then the point of tangency will be what? Point of tangency will be x0 and f of x0. And f of x0 is 1, f of x is 1 over x. So this point will be x0 and 1 over x0. Then what will be the equation of tangent line? Then the equation of tangent line will be y minus f of x0 equals f prime of x0 times x minus x0. F prime of x is, what is it? Derivative of 1 over x. f of x is 1 over x. The derivative of 1 over x is minus 1 over x squared. So f prime of x0 will be minus 1 over x0 squared, right? So if f prime of x is minus 1 over x squared, well, of course, you can find f prime of x using a quotient rule, or you can also do it with the power rule. X to power minus 1, derivative is minus 1 times x to power minus 2, which is minus 1 over x squared. And f prime of x0 will be minus 1 over x0 squared. So then my equation will be y minus f of x0 is 1 over x0 equals minus 1 over x0 squared times x minus x0. Okay, now the equation of the line will be y equals minus 1 over x0 squared times x minus x0 plus 1 over x0. Okay, so see, this is sometimes a little bit confusing for some students. See, here we have x and y appeared, right? So equation of the line, what is the general form of equation of a line? Y equals mx plus b, right? So some constant times x plus b. And this is of that form because the x0 here is a constant. Like I said, it could be 1, could be 5, could be 7. I'm not assuming it's 1. I'm not assuming it's 5. I'm not assuming it's 7 because I want my argument to be valid in general. But to get an idea about what's happening here, you can think about it. If x0 was 1, for example, then y would be minus 1 times x minus 1 plus 1. If x0 was 2, then minus 1 over 4 x times x minus 2 plus 1 over 2, and so on, right? So for any value of x0, any fixed value of x0, then you can replace it here. You will find equation of a line because you will have an equation of the form mx plus b. But if in the exam, for example, you do some calculation and you will see that, for example, that you have x squared here, instead of x0 squared, you have x squared here, then that means you have made mistakes somewhere because this is not equation of a line. Equation of the line should be, as I said, some constant times x plus another constant. But this one, if you expand, x times 1 over x squared is 1 over x. So it's a constant over x, and this one a constant over x squared. So that's not equation of a line because it's not some constant times x plus another constant. Okay, so that's the way you can check your answer. Equation of a line has to be a constant times x plus another constant, and x0 is a constant here. Now we need, what else do we need? We need to find the points A and B, which are the x-intercept and y-intercept of this line L. So this is equation of L. Next, we can find the points A and B, which are x and y-intercept. A is y-intercept basically. So y and x-intercept of L. Intercepts of L. So for y-intercept, we can replace x with 0, right? Then y will be how much? To y-intercept, I need to replace x with 0. Then I get minus 1 over x squared times minus 1 over x0 squared times zero minus x0, and then plus 1 over x0. So then this is 1 over x0 plus 1 over x0. This is 2 over x0. Two over x0. So the point A will be 0 and 2 over x0. And finally, for x-intercept, we need to replace y with 0. So 0 equals minus 1 over x0 squared times x minus x0. Plus 1 over x0. So that gives 1 over x0 squared times x minus x0 equals 1 over x0. So that means x minus x0 equals, if I multiply both sides by x0 squared, then the x minus x0 will be x0, which means x will be equal to 2x0. So the point B will be 2x0 and 0. And therefore, area of OAB will be what? So 2x0. So this length is 2x0. And this length was point A 2 over x0. So this length is 2 over x0. So area of OAB will be height times base divided by 2. So 2x0 times 2 over x0 times 1/2. And the answer is 2. So area of, it seems that the screen is freeze. Let me, okay, here. See, for x-intercept, we said that we replace y with 0 in the formula for the, we had the equation of the line, right? It's the equation of the line. And we replaced y with 0 here. And we did that, and we found the x value. We just took this term to the other side, multiply both sides with x0 squared. We found the x value. X value turns out to be 2x0. So the point B, we said, is 2x0 and 0. So this point B is 2x0 and 0. So this length is 2x0. And this length here, because point A was 0 and 2 over x0, so this length is 2 over x0. And then we just need to find the area of OAB, height times base divided by 2. So 2x0 times 2 over x0 times 1/2. The answer is 2. So this area of the triangle formed by the tangent line is 2, regardless of the point of tangency. Because see, as you can see, x0 cancels out with x0. So whether you write the equation of the tangent line at x0 equals 1, or x0 equals 2, or x0 equals 3, doesn't matter, because this x0 cancels out with this x0. The area of the triangle will be 2 in any case. Okay, so well, that's it. But I can give you some more exercises. I'll upload the assignment. But let me also give you some exercises here during the lecture, and of course, I'll also upload the assignments as usual as well. So let me give you some exercises. Just from this chapter, you know, we can give many exercises from this chapter. Just give you. I want to give you a few here. Let's say, let f of x equals x squared if x less than equal to 1, and root x if x bigger than 1. Determine whether f is differentiable at x equals 1. If so, find the value of the derivative there. Find the value of the derivative there. See, let me give you some hints for exercises as well. So this is a piecewise function. For a piecewise function, first you can check the continuity. If the function is discontinuous at the point, then immediately you can conclude that the function is not differentiable. But if it is continuous, meaning that if the left limit and right limit and the value of the function at the point are equal, if the function is continuous, then you still have to figure out. If the function is continuous, then it may or may not be differentiable. You have to use the limit definition of derivative, limit f of x minus f of 1 over x minus 1. Try to see whether that limit exists or no. If that limit exists, then the function is differentiable and the value of derivative is the value of the limit. If that limit does not exist, for example, if the left limit and right limit of that fraction, f of x minus f of 1 over x minus 1, left limit of this fraction at 1 and right limit of this fraction at 1 are not the same, then that means this limit does not exist, and then the function will not be differentiable at that point. So this is just a hint for this exercise. Okay, so next exercise. Find all points where f of x equals absolute value x squared minus 4 fails to be differentiable. Fails to be differentiable, justify. Okay, so then let's see what else. Next exercise. Find all values of x. All values of x at which the tangent line to y equals x plus 3 divided by x plus 2 is perpendicular to the line y equals x. All values of x such that the tangent line at this point is perpendicular to y equals x. Let me remind you that two lines are perpendicular to each other if the product of their slope is -1. Well, slope of y equals x is 1. So if you want some line to be perpendicular to this line, that means it has to have the slope of -1. So you need to find all the points on this graph such that the slope of tangent line at those points is -1. But what is the slope of tangent line? Slope of tangent line is derivative at the point. So just calculate derivative of this function and the value of derivative has to be equal to -1. Find all x values with this property. Next exercise. Let f of 4 equals 3 and f prime of 4 equals -5. And let g of x equals root x times f of x. Find g prime of 4. This is very straightforward, because you have g of x as root x times f of x. You can find g prime of x. And after you find g prime of x, which you can find easily using the product rule, right? G of x is the product of two functions. You can find g prime of x. using the product rule, and then find g prime of 4, replace the value of x with 4. So the only important point of this question is that if you want to find g prime of 4, first you need to find g prime of x. After you find g prime of x, then replace x with 4, okay? Same thing we said about second derivative. If you want to find g double prime of 4, for example, first find g double prime of x, then replace x with 4. All right, next example or exercise, basically. Exercise. Let f of x be an even function be a differentiable function, be differentiable, let f of x be differentiable on R, and suppose that f of x is an even function show that f prime of x is an odd function. Okay, so this relies on the definition of even function and odd function. Even function means a function such that f of minus x equals f of x for every x. Even function means f of minus x equals f of x for every x. Odd function means a function f such that f of minus x is equal to minus f of x for every x. Odd function means f of minus x equals minus f of x for every x. Now, if you want to show that if f is even, then f prime is odd. So you have to use the definition of even function and definition of odd function to show that if f is even and then f is odd. So so I wanted to remind you about the definition of even and odd function. I also want to remind you about the fact that if you want to prove a statement in mathematics, you have to prove in general. Okay, so do not give examples. You cannot say, for example, f of x equals x squared is an even function, and then f prime of x equals 2x is an odd function. You cannot give examples. Your argument has to be valid in general for any function f, which is even. Then you have to show that f prime must be odd. Okay, and then the next exercise, let f of x equals x squared times sine 1 over x if x not equal to 0, and 0 if x equals 0. Part A, show that f of x is continuous at x equals 0. Part B, find f prime of 0. Find f prime of 0 using the limit definition of derivatives. Part C, find f prime of x for x not equal to 0. Part D, show that f prime of x is not continuous at x equals 0. See, this is an interesting example because it's an example of a function that is differentiable at 0, but f prime of x is not continuous at x equals 0. So please note here that, of course, f is continuous at 0 because f prime of 0 exists. You can check that f prime of 0. You will see that after. First, you have to show f is continuous at 0. Part B, you will show that not only the function is continuous at 0, but is also differentiable at 0. So if the function is differentiable at 0, of course, it is continuous automatically. But part A asks you to show that it's continuous. Part B asks you to show that not only is continuous at 0, but it's also differentiable at 0. But then part D, you want to conclude that f prime is not continuous at 0. F prime. So f is continuous at 0. Even more than that, it's differentiable at 0. But f prime, because we know that f prime of x, we can look at f prime of x as a function itself, right? F prime of x is a function itself. And any function could be continuous or discontinuous at any point. So f prime of x, when we look at it as a function by itself, it's not continuous at 0. So for example, if in part E asks you whether f is twice differentiable at 0 or no, so f is differentiable at 0, but is it twice differentiable at 0? The answer is no, because second derivative is derivative of the first derivative. And in part D, you conclude that the first derivative is not continuous at 0. So if the first derivative is not continuous at 0, then it will not be differentiable at 0 either. So f is continuous and differentiable at 0. However, f prime is not continuous and therefore not differentiable at 0. And therefore f prime of 0 exists, but f double prime of 0 does not exist because f prime of x is not differentiable at 0. And f double prime of 0 means the value of f, the derivative of f prime at 0. But because f prime is not differentiable at 0, f double prime of 0 does not exist. So the function is continuous, f prime of 0 exists, but f prime of x is not continuous and therefore not differentiable at 0. Therefore, f double prime of 0 does not exist, meaning that the function is not twice differentiable at 0. Okay, so this is an explanation about this exercise, but please make sure you do all parts. And yeah, I will also upload the assignments, online and the additional ones. Okay, guys, so thank you and see you next time.